Okay, hi. So in this video, I'm going to explain why integrals and derivatives are connected. And in fact, they're inverses of each other. So we know that calculus has two important properties, I would say. Okay, so the first one is derivative, which is basically the slope of the tangent line of a specific point on a curve. And then we have integral, definite integral in particular, which is the area under the curve from a constant a to b. So we know this idea, both of these ideas. So now let's link it together with proving, right? So we know that a and b are constants. Let's think of b in this particular case as the variable. Let's call b as our x. So let's write the integral from a to x f of t dt. So why I wrote this, so that I will get a separate function g of x, because if our b is not a variable, this whole integral is just a number. It's just a number, because if you tell me like compute the integral of x, let's say from I don't know, 0 to 1, you can just compute and this will give you an actual number. But we here, for fundamental theorem of calculus, we want to make this whole idea as our function as a whole. This integral, we want to make this as our function. But the function like can't be just a random constant, right? So let's just name the b as our variable. So a is our constant, so it can be anything, 1, 2, 3, 1,000, million, but x is our variable. But what about t? What is t? Let's think of t as a local variable, let's say in programming, if you know programming. Why do we call it local variable? Because let me bring an example. If you want to calculate the sum from 1 to n, I squared, what is I here? It's just a local variable in order for us to be able to calculate the actual sum, right? So it is like, it will disappear once you solve this actual sum. So that's the idea of the t actually. So now, the fundamental theorem of calculus says that if we derivate the g of x, we will get just f of x. So we will just return to the function that we started with, okay? So how does this work? Let me just draw this whole idea on a graph. So let's just think this is our a and this is our x. Like at some point of the time, this is our x, right? So we should calculate from here till here, right? So the area, okay? The x, as I just mentioned, it is a variable, so it can just go from here. So it's like x plus, I don't know, p, and then we can just say like, if our function is even bigger, we can just say x plus c. So it is just the variable of the function g of x, okay? So what's the actual definition of derivatives? It's the limit from h of h that goes to 0, g of x plus h minus g of x over h. So this basically gives the derivative of g of x. So we have to prove that this equals to our function f of x, right? So let's do it. So let's plug in gx plus h in our function. And remember, this is our function, right? I know this is kind of weird that the integral is our function, but let's just write it like that, yeah? So let's plug in. So limit as h goes to 0, g of x plus h is actually the integral from a till x plus h minus, f of t dt, minus the integral from a till x f of t dt over h. right? So now, we have this part. Let me actually delete this x plus b and c and draw with the h. So let's say this is our x plus h. So this part is our, let me draw with yellow. This part is our actual integral from a to x, right? So we have to minus this whole part from this. So we will get this red part only. What's this red part in terms of the integral? It is integral from x till x plus h f of t dt. In fact, we know that h goes to 0, right? So what does this tell us? It tells us that actually this part, we know that it is x plus h minus x, so it's just h, the length of it. So we know that h goes to like 0, right? Like it tries to get into 0, like the limit of it. So this part, even though it doesn't really look like an actual, it doesn't really look like an actual rectangle, but when h goes till 0, it is actually a rectangle. So just imagine this part as a small rectangle, right? So the length, the width of it is h, and the length of it is what? The length of it is actually f of x, because we plug in this x, right? So it's f of x, right? So this is how it works. This is actually just equal to f of x times h, because we know that like the area of the rectangle is f of x times h, right? So now let's plug in it into our actual definition of the derivatives. So limit as h goes to 0, and we already calculated this part, right? It is fx times h over h. Oops, h's cancel out. So we just remain with f of x. So this is the actual proof of it. This is how it works. So basically, we just proved that if we say that g prime x is actually just equal to the original function fx. And this is the whole proof that integrals and derivatives are actually linked. Thank you.